Our next paper is paper number 71E. Title of the paper is Synthesis of Methyl Tertiary Butyl Ether on ZSM-5 zeolite. The authors of the paper are W.J. Hatcher and S.I. Penn. This work was performed at the University of Alabama. Our speaker is Professor William J. Hatcher. He received his bachelor's degree in chemical engineering from Georgia Institute of Technology and his master's and PhD at LSU. Dr. Hatcher.
Thank you, Professor Hopper. Good morning. This morning I'd like to talk to you about some recent research that we've done. And to start with, I'd like to recognize the contributions of my co-author, Mike Penn, who recently finished his master's degree and is now a doctoral student at Akron. We were interested in studying the kinetics of methyl tertiary butyl ether formation, MTBE, because of its rapid growth in the petrochemical area. As you know, it's one of the most popular oxygenated compounds to replace tetraethyl lead for octane boosters in gasoline. At the present, the commercial catalyst that's used for this is a macroporous ion exchange resin catalyst, which, according to literature reports, has several disadvantages. First of all, the present catalyst tends to decompose at temperatures above about 90 degrees C, and even at lower temperatures it slowly releases acid into the product stream, causing downstream corrosion problems. And also it tends to catalyze an undesirable dimerization side reaction. The ZSM-5 zeolite had previously been reported to be active in some screening studies, and so our objective here was to get a quantitative kinetic model of the kinetics of this reaction in order to compare the activity and performance of the zeolite catalyst with the present commercial catalyst. The major reaction shown here at the top of the slide is that methanol reacts with isobutylene to form the MTBE. Methanol is generally in excess, and the isobutylene, the limiting reactant, is in normally a mixture of several C4s in the range of 30 to 40% concentration. These C4s typically come from cat cracker. The other C4s in the mixture tend to be inert at reaction conditions. There are two major side reactions that occur. The dimerization reaction that I mentioned of two isobutylenes forming the dimer, and then another reaction of isobutylene and water forming tertiary butyl alcohol. The third reaction, of course, can be prevented by thoroughly drying the feedstocks. ZSM-5, as you remember, is a medium pore zeolite that can be characterized by this sort of two-dimensional structure. First, you have a vertical pore that is essentially elliptical in shape, with a size of about 5.7 by 5.1 angstroms. And these vertical channels are connected by more or less horizontal zigzag channels that are almost circular in diameter. The ZSM-5, as you remember, is a very high silica aluminosilicate crystalline structure, and it is presently used in several commercial operations, including Mobil's methanol to gasoline and xylene isomerization processes. Because of the size of the zeolite pores, it's useful perhaps to look at the various dimensions of our of our feedstocks. And as shown here, the isobutylene is about 3.9 by 5.4 angstroms, or 0.39 by 0.54 nanometers, and the methanol a little bit smaller. And both of these feedstocks are just slightly smaller than the straight pores and the zigzag pores of the zeolite catalyst. The commercial catalyst, typified by the amylase 15, is about 2 orders of magnitude larger in pore size than the zeolite. We studied the reaction characteristics of the two catalysts in a fixed bed isothermal integral reactor system at these conditions. First of all, the main reaction, the synthesis of MTBE, is an exothermic reaction. Therefore, it becomes equilibrium limited at higher temperatures, and in fact, it becomes equilibrium limited at some very modest temperatures. And so to try to counteract the effect of the temperature limitation, you can increase pressure up to a point, and that point becomes, of course, when you liquefy the reaction product mixture. So with these constraints then, we looked at reactor temperatures of about 75 to 115 degrees C, pressures of 300 to 600 psi, 20 to 40 bar, and the reaction product mixture was in the liquid phase at these pressures. The microreactor contained a half to 1.2 grams of catalyst, which was typically 40 to 60 mesh in size, with the reactor diameter of the microreactor of 3/8 inch tube. We fed methanol and isobutylene feed rates in these ranges, and the isobutylene was a limiting reactant in all cases, so that we had a space-time based on a mass of catalyst per mole of isobutylene per hour of 6 to 12. This is a simplified sketch of our reactor system. The reactor plus a 1/8 inch preheat coil was immersed in a sand bath for temperature control. The isobutylene was charged from a vapor cylinder into a armored gauge glass, which was cooled by a refrigerant and therefore condensed in the armored gauge glass, and then later pressurized by nitrogen to blow case the liquid isobutylene in through a mass flow meter. The methanol was charged into a burette and pumped continuously to the reactor through a high pressure metering pump. The back end consisted of simply back pressure diaphragm loaded back pressure regulator, a product cooler, and product receivers. Our first study on the ZSM-5 catalyst was to look at catalyst deactivation or activity maintenance. And this is a plot of isobutylene conversion versus time on stream. And as you can see, the conversion dropped from about 87% at 0 time on stream to about 85% at 50 hours on stream, representing about a 10% activity loss over this time period. This, of course, was run at a standard set of conditions and with a temperature of 115 degrees C. First, we looked at the effect of pressure on isobutylene conversion, and here's a plot of the isobutylene conversion versus the pressure at two temperature levels, 115 degrees C and 75 degrees C. And as you can see, pressure had little or no effect on the conversion or the net reaction rate in our study here. This is not really surprising, though, because of the liquid phase reaction. The pressure then had little effect on the reactant concentrations or the equilibrium conversion in the liquid phase. Next, we looked at the effect of the methanol to isobutylene feed ratio. This is a plot of the conversion of isobutylene versus the feed methanol to isobutylene ratio at three temperature levels, 115, 100, and 75 degrees C. And as you can see, the methanol ratio had essentially no effect on the net conversion of the isobutylene or the net reaction rate, so that in effect the reaction rate is zero order with respect to the methanol. This suggests a high surface coverage of the methanol on the catalyst surface. Previous papers had reported a first order reaction dependence on isobutylene. And so here would be in the first order rate equation with Ca being the concentration of isobutylene, Cr the concentration of the MTBE in this reversible reaction. Of course, in running our plug flow reactor, or a reactor that closely approximated plug flow, the integrated form of this equation is shown here, with X being the isobutylene conversion, Xe the equilibrium conversion, and then CaO W over FaO representing the space-time based on catalyst mass, and Xe again the equilibrium conversion. Well, in plotting the data obtained on the zeolite catalyst in that form, this is somewhat out of focus. This is a plot of this log function of conversion versus the mass spacetime. And as you can see, we obtained a relatively good fit of straight lines through the origin for the three temperature levels. So that from this we conclude that the first order dependence on the isobutylene is a good approximation for the reaction with the zeolite catalyst. From the slope of these lines, then we could obtain the reaction rate coefficient divided by the equilibrium conversion, and then from that extract the equilibrium conversion. And so here are the values from the slopes of the previous plot, and we took these values and plotted them in the conventional Arrhenius form and determined the activation energy from the slope of that plot to be approximately 13 kilocalories per mole. This compares to an activation energy of about 17 kilocalories per mole reported for the amylase 15 catalyst. This data table shows a comparison between the resin catalyst and the ZSM-5 results. And so if you look at the first column in the amylase data versus the first column in the ZSM-5 data, you can see that they were run at the same conditions of temperature, space-time, and the conversion in the resin catalyst case was 85% versus 16% with the zeolite catalyst. This represents a several-fold difference in activity, with the resin catalyst, of course, being about 5 times more active than the zeolite. The selectivity of these conditions were both high, 99 versus 100. Then you can see that we looked at the effect of going up in space-time with the amylase catalyst, and as expected, the conversion increased. But then when we went to a higher temperature, going from 75 to 100 with the amylase catalyst, we saw the conversion drop from 99 to 91%, representing the reported decomposition of the resin catalyst at the higher temperature. On the other hand, with the zeolite catalyst, as we go up in space-time, we again saw the increase in conversion, and then as we go up in temperature, the ZSM-5 catalyst maintained a relatively stable conversion, even at the 115-degree data that we saw early in one of the early slides. And so at 115 degrees, we could approach about a 90% conversion, which compares with the amylase catalyst activity over at about 75 or so, a little less than 75 degrees C. The selectivity for the zeolite catalyst was essentially 100% selective at all the conditions we studied. Our conclusions on this work are that, again, we saw a zero-order dependence of the rate on the methanol concentration and on the total pressure. We found that the first-order reversible reaction rate equation fit our data, and that the amylase 15 catalyst was more active than the zeolite catalyst at 75 degrees C, but of course it lost its activity in temperatures above 90, and that the zeolite catalyst had a better thermal stability and selectivity than the amylase 15. We also conjecture that we are seeing a high surface coverage of the methanol on the catalyst surface, and perhaps some sort of collision mechanism of the isobutylene at the active site. Our plans are that we already have underway some diffusion absorption studies on the zeolite catalyst using the reactants and products that we've discussed, and hopefully we'll have these data available in the near future. Thank you for your attention.
Just a few questions. Matthew Cox, Chemical Research and Licensing.